And let's go. So the trick where I've mentioned before that this is sort of the first of several geometric pieces of material we're going to cover. It's the most important one because area is used as a measurement of how far curves are from each other, and that's a pretty common thing to want to do. But anyway, the trick we're going to see today is one we'll keep using in the other geometric sections. And this is something we've seen a few, I think, once before at least, where we're looking for the area between curves, and the upper and the lower curve switch. So because the integral is the upper minus the lower, having those switch means that you have to break this up into two integrals. You can find this area as one integral. You can find that area as a second integral. And not always, but sometimes. There's a way to approach a situation like that using a single integral. And that's what we're going to talk about today. I hope this is what I think it is, this region I'm going to draw. I feel like I've run into problems with this example before, but let's look at the region between y equals the square root of x plus 2, y equals negative x minus 2 squared plus 4, and y equals 2. And we probably don't have much intuition about what this region looks like. Certainly I don't. So let's go to our graphing application. The forever useful Desmos. Forever useful. I think that screen might be honking out on us. Square root of x, get out of there, plus 2. Y equals negative x minus 2 squared plus 4. And this is convenient. And y equals 2. No, let me fix this. This is close to what I want it to be. But I'm going to take this horizontal line and I'm going to scoot it up to not 2, but 3. And now, let me correct that in my notes as well for later. And now we see, I'm zooming in, it's taking a while. I think I'm gonna have to start looking at alternative technologies. but you see, we've got this region here. And this region here always has the same lower boundary, this horizontal line, but the upper boundary changes. For a while, we're going up to this square root function. But here we switch, and now if we look at the upper boundary, it's this quadratic. So we go back to the whiteboard. We've got a square root function. Sometimes being the upper curve, and then other times being the upper curve. We have this quadratic. And then always being the lower curve. I changed it from when I first put the problem on the board. But y equals 3. So we could approach this problem without doing anything different from what we've done earlier this week. The way you would do it is you would break the integral into 2. And then you would have the integral from, well, I don't know actually what the limits of integration would be. Let me get this briefly back up. We're starting at 1. Swap at this messy decimal, 2.6 something, and we end at 3. So from 1 to 2.6, and then the upper curve is the square root minus the lower curve, which is 3. And then from about 2.6 to 3, the upper curve is now the quadratic. And the lower curve is still 3, and we could approach it that way. So the alternative, which you might or might not think is easier than this, is to say, well, where does the integral come from in the first place? I mean, the integral comes from messing around with rectangles, right? We've got a curve, and we draw a bunch of rectangles, and we find the area of those rectangles, and we take a limit. And as for the area between curves, it's the same thing. That's why the area between curves is an integral. To find the area find their area, and then we take a limit. And of course, we don't show that step. I mean, taking the limit turns it into an integral, but that's what's actually going on here. And, you know, if you think about it in this purely geometric way, you draw a bunch of rectangles, and then you find their area, and then you take a limit. I mean, there's no particular reason that you shouldn't do this same process with horizontal rectangles instead of vertical rectangles. And going back to here, I mean, when you draw your rectangles, sometimes they go from 3 to the square root. Sometimes they go from 3 to the quadratic. That's what's causing you to have multiple integrals, that they're going up to different functions. Well, if instead of that, you drew horizontal rectangles, that would not occur. Every one of these horizontal rectangles starts with the square root on the left and goes to the quadratic on the right. So what this means is that if instead of an if, let me write this down, instead of an upper and a lower curve, you have left and right curve, then the area can be written as the integral of the right curve minus the integral of the left curve, but instead of integrating with respect to x, you integrate with respect to y. No, ordinarily, when we write the rectangles this way, the width of the rectangle is written dx, and when we take a limit, sorry, it's written delta x, and when we take the limit, those dx, those delta x's, geez, can't speak today, but those delta x's turn into dx in the integral. Here, instead of delta x's, instead of horizontal distances, we've got delta y's, we've got vertical distances. And this turns into a dy when we take the integral. And I wouldn't ordinarily write this, but just for emphasis, our limits of integration are also now in terms of y. You know, when we have a situation like this, we start at x equals a, and we go up to x equals b. Now we're starting here at y equals a, and we're ending there at y equals b. And what this means, and kind of the downside of this, is that if you're integrating with respect to y, and your limits of integration are also with respect to y, well, what about these curves? these curves have to be functions of y as well. So there's a trade-off involved here. You know, going back to this example and saying, well, we don't want to do this in terms of two integrals. We'd like to do it in terms of one integral. Well, the really sort of nice dream would be to say, well, we start down here at 3, and we end up there, which I'm going to use Desmos to tell me where we wind up. We wind up here at some not terribly appealing y value, 3.6 or so. And let me, because what I'm about to write on the board isn't true. And we say, well, our right-hand curve is this one over here. And our left-hand curve is this one over here. And now we can just take a single integral, but as I say in big capital letters, this is incorrect. It doesn't make any sense. We're starting at y equals 3. We're ending at y equals 3.6. We're integrating with respect to y. So what are all of those x's doing inside the integral? So there's a solution to this, at least in this particular problem, there's a solution to this. That solution is that, well, you can write this curve, you can rewrite this curve so that you have y's instead of x's. That is to say, you could subtract 2 from both sides. And then you could square both sides. And I mean, there's some sort of one-to-one stuff going on here, but for intents and purposes, for as far as we're concerned, this is now the same curve. It's written with y as our variable instead of x. No, go back to Desmos. X equals y minus 2 squared. You see this this curve here. If we can hide that first equation, and now we've got this left-hand side written in terms of y. And we can do the same thing for the other side as well. For this side, it's going to be messier because the function we're working with is messier. But if we start with y equals negative x minus 2 squared plus 4, Now we can do, in theory, an algebra student could do this. I don't know how much joy most of them would have in reality, but we can take the 4 over to the left, and we can multiply by -1 to get rid of that negative sign. And now, so this isn't actually 1-to-1. So there are actually two things we could do. We could take either the positive square root or the negative square root. Now that's a problem. We need a function. We can't integrate plus or minus the square root, but it's a problem we'll solve in just a moment. Take that 2 over. And all that this means, again, this is a problem. It's a problem we're about to fix, though. One of those square roots is going to give us this part of the parabola, the increasing part over on the left. And the other one of those square roots is going to give us the decreasing part of this parabola over on the right. So 2 plus the square, what was under the square root?
4 minus y.
4 minus y. So as it happens, that's this plus is the one you wanted. I don't know how well you can see that. This curve in black is covering up now the right-hand side of this. And if I started with 2 minus that, I'd have gotten this curve over here, and I'd have said, oh, well, that isn't what I wanted, and I would have corrected that error. So now we see we still have the left-hand curve. We still have the right-hand curve. We have an upper bound, we have a lower bound. We can write this as a single integral. And after all of this work, I'm not necessarily convinced that this is easier than breaking it up into 2 integrals, but there's 2 plus the square root of 4 minus y. And there's y minus 2 squared. dy. We're starting still down here, this horizontal line at y equals 3 is our lower bound. We go up to that point, and that 3.6 is our upper bound. So we have successfully written this as a single integral. The bad news is, at least depending on how good you are at mental integration at this point in your game, we might then have to break this up into two integrals anyway, in the sense that what we have here is a little u substitution. U is this 4 minus y. Du is negative y dy. And when you combine u substitution with addition and subtraction, that ordinarily means we're going to have to break the integral into two. Because here we can't, I mean, maybe we could try to do something clever, but on the face of it, we can't rewrite this y minus 2 in terms of our u. And doing u substitution means you have to rewrite everything. So in this particular case, we are, I don't know why I put the integral there. In this particular case, we're probably going to have to break this up anyway. But, you know, it varies from situation to situation. I mean, in this particular example, it would have been feasible. I have to keep looking. In this particular example, it would have been feasible to do it. But I mean, if you have something like I don't know, I mean, if your curves really look like that, maybe you have something like x equals the sine of y, and x equals negative the cosine of y plus 3, and you're going from x equals, or from y equals negative 4 to y equals positive 4. Here you really couldn't use vertical rectangles, because if you try to draw vertical rectangles, they break, right? The vertical rectangle would go from here down to here, and then there's this break, and then the vertical rectangle keeps going. Whereas using horizontal rectangles makes perfect sense. We would not at this point in our career be able to deal with it because we can't integrate inverse trig functions, but we can at least see that we can draw horizontal rectangles, and they always start with this sine and they always terminate with this cosine. And here, horizontal rectangles would be mandatory. So I'm obviously looking at this particular example and expressing a little, you know, ambiguity, whether this is easier than vertical rectangles, but you don't always have a choice. And that's why this material we have to learn, because it's not just convenient, it's sometimes necessary. And with that, I mean, I guess unless someone tells me they really want me to finish out this definite integral, I'm not seeing a frantic show of hands. So with that, we'll end today's lecture a little early. Congratulations on your first week of Calculus 2. I will see you, of course, Tuesday, Monday being Martin Luther King Day. Please be careful out there. It's expected to get extremely cold.